That's okay. So thank you to all of you to there. So this is a joint paper with colleague. This woman. She was my PhD student, and Christy was the second supervisor of Huong. And so we began to work together 8 years ago, more than 8 years ago. And we continue to work together for well, this paper is quite a long story. Because this paper is taking so many years to understand where we are from. So this is a very critical paper. Because this paper, in fact, was between ideas from Christine, ideas from me, and then we had Huong. And Huong wanted to do at the Vietnamese Institute for Advanced in Mathematics. So, me, I had the idea to do something about climate change. When I was reading the literature about climate change, I was not very happy by seeing a common approach to all the papers I was reading. And the difficulty with that approach is that I wasn't able to trust it because they were not taking into account what object, but what mathematical object they treat. And thanks to Christine, my colleague from Toulouse, we find an idea how to treat it. But we need to invest in some mathematical tools in order to do that. And so this paper tries to summarize all that. So when you are working in climate change, you have a key ingredient. In all papers about climate change, the first thing the authors are doing is to evaluate the need between one outcome, say for example, and the weather. And so they want to estimate that. So here we have someone very famous if you want to work on climate change is that man Simioni. Simioni has a chance to have a lot to have a big team. And one of my jobs when we read this paper was to find who is the recommendation in the list of the 1204 papers. And I found who is the recommendation. So you can move to the second. And so when you read this literature, so just mathematical fields, when you read this paper, so I'm working in doing research for estimating the family function in agriculture. So my object of interest is to estimate the relationship between crop yield, say RiceYield, Vietnam, so they have data about that, and then weather. And when you are studying that kind of relationship, what is important for the crop to grow is the temperature, but not the average temperature. Is the way temperature accumulates. Okay? And then is that the response of the crop to different levels of temperature will not be the same. And so you have two famous papers published in 2009 by two authors, Michel and Prof. And they propose to estimate this one. So maybe you are not used. This is a regression model. But so you have compute. You have the density of temperature. And you have the response. And you see that you take into account that this response can be different when considering different range, the range of temperature. So you have a minimum temperature, maximum temperature, and the response here will be different, depending on the level of temperature. This is is a strange object. You are not used. I think that you had the lecture in econometrics. Maybe some of you by Huong. I do not recognize some of you, so not like me. But you're not used with that. You are used with a linear model. If you are like a local data, with ZX and so on. And what is quite unique that I presented this paper in a conference. So my colleague Christine went to be retired, and we organized into the conference in his honor, and I presented that paper. And someone said to me that the first editing, the idea to write the regression model that way was Fisher in 1924, 1 century ago. In a paper published in this journal, you can find this paper, and he called that the regression integral. So I hope you have some knowledge in mathematics. Well, you have an integral. What you know is if you want to compute the integral, you can take an approximation. So you can say, for example, that the temperature will be 1 degree to 40 degrees. And for each degree, you can take an approximation of that by taking the probability of that. That is the quantitative between the value u and the value u plus 1. And then here, you have a response depending on the value of u. But here, you have now, as you are taking 1 degree, 1 Celsius degree B, you have here as many parameters here. You have chosen the corresponding to the number of u. But what is this? This is the number of temperature smaller than u. This is the number of temperature smaller than u. And when you have that, what is this? It's simply the histogram. You are counting the number of days falling in the interval. So here you can choose degree, by degree, you can choose what you want. But you are only counting. And so this gives rise to a huge literature. They work out in this literature. And you have a very good paper by Platter and Simioni, where they are using histogram of temperature. And so I began to work on that in a big project about regression in Vietnam. And at the beginning, they asked me to give some insight about the literature. So I read the literature. When I saw that, I was not so pleased. Because what people are doing is that you have a number of bits, say 10 bits. So you know that the number of days in the 10 bits are 360. So if you want to estimate that, and you put it up, there is a problem of multicollinearity. So they drop 1 bit, and they say the temperature, the impact of the temperature, say drop the first one, the impact of temperature in the second bit will correspond to add 1 day in this bit with respect to the bit you choose as the reference. You can do that. But me, I was not satisfied. And this is what motivates this paper. I was trying to find an approach where I can tell a story about climate change without doing that. And you can move to the next slide, please. And so we have to find a strategy. And if you read the paper by this woman, the Kenyan woman living in the US, and Solomon-Sian, they were the two first to say that when you have a histogram is not in what you are used to. You are used to when you are doing statistics, when you are doing mathematics, you are most of the time used to thinking about, how with a given dimension, with pure numbers. But here we are working with variables that are constrained. That is, if I take the different bill and I sum the value in the bill, this is 360. smaller space because we have one constraint on that. And this space is called a sample. So, with my colleague, Trinh, we worked on what is called compositional data. So, the idea was to use compositional data instead of using, but it's taking a different view of the histogram than the view people are taking in the histogram. And why using the histogram when we can use continuous search? So the difficult part of what we have done is that this when you use histogram, so you can move like this. And so we will in this paper we will use the discrete approach, where we will consider the histogram as a composition. So remind that is an object such that the sum of the different elements of this object is equal to 1. And we will compare that with an approach taking the density as the exploratory variable, where we have an object so that the interval is equal to 1. We will address this issue unfortunately by using pyramid. And this is where we have problems. And I presented this paper in front of
mấy bữa nay làm những đi làm
in
kia muốn dỗ đó cái đường đi mà kẹt rồi đâu
in the audience, a specialist of climatic objectives was there. And he said to me, you must use US. So I tried to convince my course to use. And it was difficult for me, but we have to use it. And so, and you will see that using that tool, we can build a climate change scenario and evaluate the impact. So for this moment, this part, I'm not so satisfied with. So maybe now I will go quite quickly. So compositional data, the discrete case. What is the histogram? Capital D means such that when you take the sum of all the components of this vector, the sum is equal to 1. So this is the same case. Good example. I began to work on that with a PhD student and Christine, dealing with the French car market. And the data were simply the share of each brand of car in a given segment. Okay. Then we generalize that for studying nutritional data. So, what is important to know is that when you have compositional data, you cannot use traditional in the equation. Because the sample, you are not in R. You are in the sample. You have to take into account this constraint, but the sum of the elements of the vector is equal. And so, you have people in the literature, Hutchinson, who propose to build the mathematics of this space. And he didn't create continue. The idea is very simple, is that you are in the same place. Which link you can build with R? If you are able to have a link with R, you will do the statistic approach and the economic approach in R, and then you will come back to the space assembly. And so the idea is very simple, is to define transformation of your data. And to find the good transformation in order to go from simplex, like S, to R, and then to come back. And so you can move to the other side. And so these are the mathematics. But here you can forget most of the things. But what is important when you are working on that kind of data? Maybe when you were a student in econometrics, you had a teacher saying to you that when you have a example, you want to explain between 0 and 1, or 0 and 100%. You are taking the log. Remember the log of the share divided by 1 minus the share. What do you see here? The share x1 for the first component of the compositional divided by this function. What is this function? This function is simply the geometric average of the share. And what is important when you are working with density with histogram is that when you are moving something in the histogram, the move is relative. You are not moving with respect only to one thing. And you will see that when you consider climate change, you are moving the distribution. So it's not simply the fact of putting one more observation in one beam. It's that you have a global move and you have to take what. And so there is a mathematics with inner product, maybe you are not using. But you know, when you are in R, when you have your vector of parameter beta, when you have your vector of external variable, what your teacher is writing as x prime times beta is simply scalar product between the vector of x and the vector beta. So no more complicated. You can move to the okay. Then this has been generalized to density. And to density, this is called the base space. So you see that we have function now, positive function, square integrable function. But now the constraint, the sum is becoming the integral. And so they developed mathematics. So I will not spend my time on that. You can read the paper, take some hints of theory. You can move to the other stage. And me, I need a lot. And they did the same. This literature is the literature 2020, 2021. Very interesting. And so they developed the same idea to find a way to go from a space where they define the given mathematics to a space where we can do what we want, because this is the space of square integrable function on the interval AB, but sum to 0. Why they sum to 0? Remember that we go from this great case, we go from the same place to R to the power B minus 1. So the constraint sum is equal to 1. From the constraint is one dimension. Okay. So we can do. And then this is how to do things. We have to estimate function. And maybe you are not used with that, but a natural tool to estimate function is to take approximation. And a very natural tool when you have to take approximation of is what is called splines. Splines are a set of functions. If you want me to define, for example, what is a cubic spline, the cubic spline is the sum of a given number of parameters with a time of the spline. The first spline will be 1, constant. The second will be x. The third will be x to the square. And then you have to define your different points, named knots, where you are taking x minus naught to the power 3, because we are working with time. Define on a given interval. So you have to imagine that we are taking the sum of functions on given interval with x defining where we are taking that. And what is important, thanks to the mathematics developed by Michel and Trinh, is that we can go from this space where we do not know what to that space where we know that this function belongs to that space. In this space, we can define a spline representation. We will have special spline in that space. And so we can come back to that. Okay? This is quite complicated. You can recognize that because we are using what's aim at that kind of tool, there is a very old book. The cover, me, I always remember the color of the cover of my book when I read the book. It's blue. So I had to find the blue book. But this is very well explained. So these are technical. This. And so this is what is a spline. So forget that. This is a spline in the space where you know where you have. So the spline is a function. And then when you have a value here, you will take, no, you will take the value of the function, this function, and you will sum, and then you have parameters. And so what you need is to know this parameter. But you have the sum of unknown parameter times things you know. And you put that in a regression model instead of the function. So when you have that, this is the parameter model. You have only to estimate. Okay. But this parameter will be different. Okay. You can move. So this is a way to do that. You must, when you are doing that, you must put a penalty. So this is what I explained to you. But I have spline, I have parameter to estimate. So I will find this parameter by minimizing a usual linear regression criterion. But you have to penalize because this estimator can move a lot. So you have to put a penalty, on the you can move to how many minutes you can move to, right? So thanks to my colleague Huong, you have here an example of what we have done. So you have here what will be our data in the discrete case. So we have to imagine that for this province, for each day during how many years, we have daily observation for minimum temperature, maximum temperature. Here we did maximum temperature in Belgium. And you have the discrete version of the density and the continuous version, continuous estimator of the density. So this is simply by counting. This is by estimating the model. Okay. So these are our explanatory. I'm right. So the data. So we want to explain here by temperature. Okay. So here is a figure about the evolving of yield over 30 years in the 63 provinces in Vietnam. We do not use individual data, we use data in N by 2. And you see that there is a beautiful trend. So the RiceYield improved from 1987 up to 2006. Okay. So we want to have a model linking yield to temperature. We will add the control variable to take into account that we have trend in the data. We will add the trend to our data. Okay. So then we realize that when you are looking to yield by economic relation, you have difference among the economic relation in Vietnam. So we will take into account that by estimating the relationship between temperature and yield, by taking into account that we have a province in that region or not. Okay. So we take into account that. It's very small. This is a test, And so these are the data sources with respect to the weather data. So coming from different most difficult part was to be able, because you know you have a grid, Vietnam, and then you have to aggregate that at the electron level. So this was done, I do not remember if you did that or by my over here, did that. But we use a kind of approach to smooth that data and then to have data for each province by taking point in the province. This was and so here you have an idea about the distribution. So you have the maximum temperature program, administration. So it was different. So this way is the difficult issue is that you have this minimum temperature, this maximum temperature or maximum temperature. And you see that sometimes we don't have that of the provinces because they are located in the south. And so we will have to treat the problem that we have seen zero in our data. And we did that by putting a small value in each bin here for provinces where we have no observation. So thanks to Huong, this is the kind of object we treat. Okay. And now Huong is working on a very interesting project to try to find the relationship and how this estimated density has moved during time. This is what you are with. Okay, you can move. So now I think this is an interesting part of the talk. So the model we want to estimate. So we have two different models, the discrete one and the continuous one. So you remember that I put an integral, and say for the histogram I will have a sum. So we will have for each compositional data. So G, the compositional data. So imagine that we have maximum temperature. We will assess the impact of maximum temperature by a given vector theta. And we will have minimum temperature also. So we will have a second compositional data. For each, we will have an histogram, the X. And this is simply the scalar product in the Archie-Stone scalar product that is here in the sentence. And so we have this scalar product between a vector and a vector. Okay. We will add some control variable, scalar variable, and we want to explain. We will do the same for the continuous domain. But now the difference is that here, instead of having discrete vector, we have function. And here, we have a vector. We keep here the same control variable. And so we will estimate this model. What is important is that thanks to the mathematics developed by people treating the discrete and we can go from this scalar product. I think I put that to the next slide. We can go from this scalar product to this scalar product. That is, we will use a transformation. You know, we go from base space, where the density is defined, to a space where we can approximate our function by spline. So here we will have an estimate of this using spline. Here we have an estimate of this in spline. This is a known value, data, so we can estimate all the parameters. This will be an unknown function of spline that are known with unknown parameters. So our problem which look to be very complicated. What is complicated is to code. So one is an impressive job. But what is that we are going from a problem that seems to be untreatable to a problem we can treat And so we put as scalar variable time, precipitation, variation on the means. And after testing the inclusion of interaction between density, and minimum temperature, and the 6 regional degrees, we decide to integrate the relationship interaction. So it's only for Red River and no friends and so we can move to. So these are the results for the parametric part of the model. We are very pleased because and no impact of precipitation. But this model now is, a model to make this way. If we want to go deeper in this model, we need to put more effort. But the interest was to be able to do something, compare. This is what we have done on the other side. Compare the result of this model. So here you have, the square of errors, the distribution of the square of errors for the different regions in our regression model, for the smooth model and the discrete model. And you see that the quality of fit is really better when you are using the model. This is what we were expecting. Because the discrete model is an approximation. And so when you are using an approximation, you are adding an error due to that. Okay. So we were expecting that. So you can move to the next slide, please. And this is the difficult part of the paper, interpretation. So here, what I want here is the transformation of the vector of parameter beta in the discrete model. Remember the beta G scalar model using one transformation named the CLR transformation. And we realized with Huong and Trinh that it's not easy to interpret that. But what are we interested in? We are interested, when you have density, you are interested by rotation. So you are interested by the weight of each beam, in the beta vector. And what you are interested is to see that when you move that way, where are you moving that way? Because you are in the density. So you are taking into account relative change in the density. Okay. And here we realize that we are in fact quite over that. That is what is interesting is to see if you have a move like that and a move like that in adjacent beams, not in beams that are too far. And you see that when you look, for example, to vector delta, something is happening here. When you have temperature between 31, 33 and 32, 33. You have a big contrast here between them. So this is a place where something is happening for vector delta. When you are looking to your first sample and you see that this is less obvious. That something is happening 30, 31, 31, 32. The same for overreaching. If you go to the impact of minimum temperature, so this is larger, but the range is smaller. You have less important impact. But we have to go deeper in the interpretation of that. Then, here, you have the same, but for the continuous mode. And what we realize, in fact, is that if when you are looking into that, you are able to interpret that, you are very good. Maybe one is more involved in that. But we put, so you have to be different ways to represent. You have to represent region, you have the impact between 32 and 33, corresponding to what we have seen for the river data. And for the river over region and the NCC, you see that we have this impact, but we translate it, we move the impact to the left, and the size of this impact, we were surprised by that, and we have a lot of this. If we have to find a way, and maybe my colleague Christine and Huong, they are mathematicians, have a better idea of that than me. We have maybe to interpret that. But something is happening here, the maximum. Okay. We can move. And then, next. And then, I have time? When we move to how to use that kind of approach in order to evaluate the impact. So we have data up to 2016. And thanks to a paper written by a man in charge of climate scientists. We were able to get, for the RCP 2.6 scenario, so the most favorable scenario, but also for other scenarios, we were able to get an histogram of predicted temperature at the end of this century. Okay, so you see that when you are dealing with climate change, you are not dealing, with the change, marginal change in some field. You are dealing with a large change, a kind of move in the distribution here. Here the distribution moves that way. Here the distribution moves to higher temperature. Here the distribution are less. And so this is why I say we have to take into account relative things. Because we are interested by the relative things that are happening in each field, And so this was what we used then to simulate for the sake of infrastructure. And this is what we use to evaluate. Because for each province, we are able to compute this change, relative change. We have the initial density. And so the change will be, driven by this direction. And using the mathematics, we can compute that. And thanks to the transformation, going from the space, the simplex or the base space to a space we know, we can compute that. Okay. So we will compute to evaluate this, and to add this to this. Okay. And the results are, so is we use simply the model we estimated. We have estimates for max. So this. We have, say, for the smooth regression model, we know this value, so we can compute that. Okay. Thanks to the linearity of the model, this is only and for the linearity of the linear product. This is simply, we can know that. And so the results are on the next table here. For the discrete regression and for the smooth regression. We spend time trying to estimate the standardization. We have the linear regression model when we are in either R or E-1 in the space of continuous function that we before. So we did the plot here. So Christine and me, we brought them and then you see that when you are looking to the discrete variation, on average, the change is not. So this is what we get, and sometimes we have negative change, but not significant. Okay. This is the discrete mode. I have to tell you a story, but I work a lot with people on estimating on estimating the impact of climate change and the distribution of income using the histogram approach in the classical. So we try being with 1 degree, 2 degree, 3 degree, and the results were very sensitive to the number of the and you see here that no impact. But when you have a look at regression, maybe you see that now we have very good value for some provinces. Why we have this big value? Because we realize that the move of temperature is, for some of the red river data, the move of temperature in the place where we identify very huge impact. So you will have more observation in that part. Time, a part of that parameter whose value is very. And so this is the reason why we are getting so huge value for red river data and for some high island and our observation. But in fact, this is the kind of result we can obtain. So don't ask me to give more interpretation of result, because this is, something we have done to compare with what, and to see what is happening when we are using it. Okay, and then I can. So we compare the compositional approach of correlation of Scarla or RiceYield on density objects. We apply that to the concrete case study of the impact of climate change for RiceYield production in Vietnam. So as you have seen, we have a type of integrated framework where, and we say, we know that we don't know because the mathematics are what we are. And this is important, and because I do not think that most papers dealing with the estimation of damage function, I think they do not know what they are. And I have to say to you that I participated to a project in climate change in Vietnam, and I read the paper published by people every time. Thanks for them, I was not so ready. Okay. So you can criticize what we have done because we treat, rice production as if the growing season was 1 year. And you know that in Vietnam, you have 2 and sometimes 3 different growing seasons. We can do more complicated things. Okay. To have a better model. That this will add complexity. Okay. So the modeling will be interesting to put some interaction between minimum and maximum. This can be done. We can go further in the comparison, but in index comparison, controlling what we are doing. We must use some non-mechanism. Okay. We can investigate the city where look, question that represented the most favorable person. Because sometimes the figure we obtain for less favorable person were we can go to the last slide and the surveillance. So here are the concept. Okay. And we did that job Yeah. So we spent the time, a lot of time in December 20 to work on that issue. But where I'm very pleased in this collaboration is that you have to put mathematicians and you have an economist. So the meaning of that is that me, I'm used to work with people. I was very pleased that one with mathematicians. And can be also a good econometrician because okay. Sorry, I was okay. Yeah. We are doing that because the model at the end, yes, it's linked to partial linear because we are taking an approximation. But to define what is new is the way we define the non-boundary. And it's not so usual because we are not using a traditional way, but is a simple line taking this line. But we use the right plane with respect to the object we are doing. This is what it is. But you're right, it's linked to partial nature. Maybe you are thinking about it. But here the important part was to use the right estimator for the. This is the reason we went to achieve some originated by touch. Yeah.